laptop troubles and HDMI troubles. Today's session is about back to basics, and I'm going to do something a little bit different, which is I'm going to whiteboard for you so that you can get the core concepts of how Ethernet TCP works. Those of you who've been doing it for a long time, you can go back to doing your email. But for those of you who may know TCP, sometimes it pays dividends paying attention, because I have yet to go to a class where I didn't learn something new, right? I just learned, talking to Mr. John Piddle here, that Vienna used to be the capital, or the centerpiece for Roman Empire after, right? So I didn't know that. So you learn something new every day. So do pay attention if you can as I hit some of the basic concepts. And the reason why I want to hit the basic concepts is because I've been at it a long time, and after so many years, you start to understand where to look for problems, right? More and more, earlier this morning in the keynote, we were talking about how TLS 1.2 is going to pose a great challenge for everybody, right? Never mind 1.3. So you can forget about payload-based packet analysis for TLS 1.2, which is going to be vast majority of the, if not all, web traffic. You still have SMB, you still have or DHCP, DNS issues, etc. But even though I've been doing this for 25 years, that gives me a little bit of latitude in saying, I think this might be the problem, and usually I can find it. But I can't teach that in a session, not even one day, not even 1 week, and probably not even a month, because there's more art to this than there is science. One day, I'm sure machine learning will catch up where Jasper, myself, and other presenters will become a moot point, right? Until that happens, you have your brain to lean on, and the only way you can do that is if you keep practicing and open up packet analysis wherever you are. If you're at an airport, open up WIreshark and capture and see what's going on. If you're on an airplane, that's one of the extreme environments where there's a high latency, and you'll see all kinds of odd stuff. When you're at home, and you're if you haven't done this, you're not a packet head. Open up Netflix, open up Hulu, open up YouTube, and do a packet analysis, see what happens, right? YouTube, for example, changes servers middle of the conversation. You would never know that unless you did packet analysis, okay? So that's a great way to learn, see what's going on. The other one is you have to read. And when I say read, if you don't want to learn something new, you're in the wrong business, right? Technology is like dog years. Every year for us is like 7 years for everybody else, okay? If you think about what happened, and I'll give you some examples. So if you assume, and I just saw this on a TV show yesterday, and I was laughing my ass off. I'll edit that out, that's okay. They were talking about, the long history of the United States. And a comedian said, hey, if you assume that at any generation somebody lived to 100 years, let's take that as granted, then it was only 3 peoples ago the U.S., the Constitution, Declaration of Independence happened. Think about that. Only 3 generations ago that U.S. signed a Declaration of Independence, and here we are. That's not a long time, right? So the reason why I'm saying that is because despite 300 years of U.S. history and thousands of years of 5,000 years in China, obviously here in Europe, everything is older than anything in America. So all I'm saying is you have to build that foundation by reading and attending SharkFest and applying it. If you just sit back and listen and you never apply it, it doesn't go anywhere, okay? Those of you who've taken calculus, differential, linear, etc. in college or any course that's of significance or difficult concepts involved, when the professor's up there drawing it out and doing it, you're like, I got it. And then you go home and you're like, what the hell is going on here? I don't understand anything. And you can't do your homework. Same thing is with packet analysis. So the good and the bad, it does take time to learn this stuff. But the good is that all these packet trace files will be available, the recordings will be available for you to apply it at home. So sit back, don't even take notes, just try to absorb as much as you can, because you can always go back to this recording to see what the hell it was that I was talking about. Make sense? Okay, So let's go to the basics, and we're going to, damn it. That one's not on me. Still plugged in. Let me unplug it and plug it back in. For those of you watching this on YouTube, we're having technical difficulties. Or projecting. There we go. All right. All right. So we're going to go with whiteboard here. So you should be able to see that. Let me just do a test. Yep, you can see that on the top, right? All right. So this is my new toy. I saw Jasper's laser pointer that was kind of built in. I thought, wow, that's cool. How can I do one better? So I decided to buy this smart pen. It's just pure competition, nothing else. So the first thing I want to talk about is Ethernet, okay? And I'll make a note of saying that there's a book by Charles Spurgeon called Definitive Guide to Ethernet, and I think it's volume 2 now, that goes into every detail of Ethernet that you ever wanted to know. Why should you care? Because when you're doing packet analysis, in reality, you're looking at Ethernet frame and up. So you have to understand these underlying topics to be able to extrapolate data from what you're looking at, whether it's TCP or IP, etc. And today, in this session, I'm going to show you what Ethernet looks like, but how IP comes into play and how TCP analysis comes into play. But we're going to build up to it, okay? So what's the packet size for Ethernet? Anybody know? Shout it out. What's the maximum frame size, not counting jumbo frames? What's an Ethernet frame size equal to? 1518. Do I have another number? You've heard maybe 1514, right? Any other takers? 1518. Everybody, show of hands. How many of you say 1518 is the right answer? All right, most of you. What if I told you you were wrong? Why are you wrong? So let's draw it out, okay? So Ethernet, that's pretty cool, right? I'm going to sit here and doodle all day. So the first thing that happens here is what's called a preamble. And there's a history of why the preamble comes into play. And then so that's 7 bytes. And then there's 1 byte called start field delimiter. Okay? And there are some historical reasons why between Ethernet DICs and this standard that does that. Then you have the destination MAC address, and that's how many bytes? 6. And then you have the source MAC address, and that's 6 bytes also. And then you have the type field, that's 2 bytes. Okay? And then you have 1500 bytes, 1500 bytes for the length. This is commonly called the MTU, maximum transmission unit. So 1500 is the maximum data that Ethernet can carry, discounting all these header fields of source, destination, etc. Okay? So that actually equals 1518. If you do the math, that's 1518. But behind that, I'm sorry, we've got to count the 4 bytes of CRC. And that comes out to 1518, except for the preamble. People forget about the preamble and start field delimiter, which is 8 bytes. Okay? So I'm going to go with 1526 as the actual frame that hits the wire. It's important if you're doing bandwidth analysis and you're doing detailed analysis, because those extra bytes add up when you have hundreds of thousands of frames going on the Ethernet wire. Okay? And so this preamble start field delimiter, you don't see it. That happens at the feed, at the Ethernet driver level. You don't even see it, and you're not going to see the CRC at the Ethernet level either. That's all taken care of for you by the network card itself. Okay? There is one thing on the Ethernet side that I want you to look at that's different. And this is something that most people, when I say, go, huh, didn't think about that. Other protocols, okay, have a delimiter. It says, I'm done. I'm done talking to you. There is no delimiter in Ethernet. So how do you know when the Ethernet frame is done transmitting? You don't know. Well, actually, you do. How do you know? It stopped transmitting. That's when you know. Okay? When Ethernet stops transmitting, it's done. Until then, you don't know. Okay? And that's because there is no concept of X on, X off, back in the old days, right? And any old protocol where you have I'm done transmitting field. Okay? So that's why back in the days, doing packet analysis on a shared hub was interesting because there was all these things called collisions and whatnot. Historical stuff, nobody cares about that anymore, but that's something that you need to understand is, hey, there is no beginning, or at least there's no end to an Ethernet frame. There is a beginning, which is the preamble and the start field delimiter, but there is no end. Okay? So that's Ethernet, that's the baseline. And here's quick trivia for you. Network General Sniffer, when you first used it, always showed the destination MAC address first, and then the source MAC address after that. Okay, so if you see like Jasper's column definition, he's got destination first and source second. That's because people who grew up on sniffers, that's how we were used to seeing it. Over the years, at some point I flipped over and I went source first and destination as a second column. Okay, so a little trivia for you. But let's go back to TCP IP. All right, so we're going to go up from Ethernet and go up to TCP IP. So the common definition of TCP, right? What are some of the textbook definitions of TCP that's different from UDP or any other protocol for that matter? TCP has what characteristics? Connection-oriented. That means send, SYNAC. I have to knock on the door and you have to answer before we can start talking. So that's connection-oriented. Perfect answer. What's another textbook answer for TCP? Reliable. So we're going to hit on that in just a second. And you know, when you're first starting out, you can rattle these things off because you read it in a textbook, you heard it at a session, and people say, oh, it's reliable. But how is it reliable? What's the mechanism that allows TCP to be reliable? Okay, which is, I think I heard sequence numbers. Is that right? Okay. So we'll talk about what that means in a practical sense. All right. So what else is there about TCP that are textbook answers? So we did connection, send, SYNAC, ACK. That's the connection-oriented part. Reliable, that's the sequence numbers and retransmissions that makes it reliable. What's the third one that TCP has versus UDP? Flow control. Okay, that's perfect. It means it can throttle itself. It can increase itself. All right. What else? There's one more that's important, and it's important when you're doing packet analysis or application level troubleshooting. I'll give you the answer. Stream oriented. Okay? What does that mean, stream oriented? So the easiest way to think about TCP/IP packet analysis is think of a garden hose. All right? So when you do the send, SYNAC, you create a hose, and all the application sends data through it. There is no beginning, there is no end. Okay? This application sitting here, this server, whatever it is, can spew data into this pipe for as long as it wants. It never has to close that socket. No one forces it. Obviously, modern day, there's firewalls, etc., but it's stream-oriented, meaning applications give data to TCP in a stream-oriented manner. There is no beginning, there is no end. Okay, it just keeps spewing. Think of it as water. You dump the water into a funnel, and that funnel puts it into a hose, and it reaches the other side. Does that make sense? Okay. This is what I meant about we're going with the back to basics because we're starting at the very basics of TCP. Now, let's talk about reliable and non-reliable for UDP, for example, right? Poor UDP always says it's not reliable, you can't use it, etc. It just means that it's up to the application to recover when there's packet loss. That's all it means. Okay? UDP is no fundamentally better. There's nothing magical about TCP that makes it reliable. All UDP is saying is, I'm not going to worry about packet loss. You have to do that. Okay, and there are many application examples that uses UDP to do exactly that. So there's nothing wrong or worse than UDP versus TCP. It just, that's what it means. So let's talk about how TCP makes it reliable. Okay? And the best example that I'll give you is, and it's maybe it's a bad example now these days, the world that we live in, but if you came home one day, and you'll have to kind of bear with me, and found out that your family's kidnapped, and there's a ransom note on the on your table that says, hey, your family's been kidnapped, but if you deliver this letter to, I don't know, the mayor, I don't care, then your family will be freed. And the only thing that you have to do is deliver this letter to the mayor, and your family goes free. Before you send that mail, because obviously it's, it's too far away, you can't walk it, you have to, drop it off in mail, etc. Before you send off that letter, what would you do? It's the only letter you got. Your family's lives going free depends on it. Okay, what would you do? What reasonable precautions would you take before you sent off that letter? Make a copy, because if it gets lost, you have another copy that you can send. This is exactly what TCP does. So let's look at it from a multiple concept of how TCP does this, okay? So the first thing we're going to do here is that we're going to assume that the server sits on this side and the client sits on the left-hand side, okay? So we have a PC here, and then we have a server here sending data, okay? But in the world of TCP, there are two buffers that we have to worry about. On the client side, that's the receive buffer. And then on the server side, we have the send buffer. Okay. So I asked Gerald earlier this morning, what's the one thing you would change if you had to go back in time? And he gave us the answer about maybe using a different language than C. Okay. So if I were to go back to when TCP/IP was written, there's one thing that I would have asked of those folks. Expose the send buffer in the packet, right? Because unfortunately, the send buffer, which turns out to is pretty important in the TCP performance analysis, is not exposed anywhere other than to the server and the application itself. The receive buffer, this guy, is the TCP window size that we all know, and which we'll talk about in just a second. Okay? So that's easy to see. That's on the wire. The send buffer, though, is not on the wire, and it's going to matter. Okay? So let's talk about why the send buffer is important. So I'm going to do is draw a buffer of one more. Okay? So there's 1, 2, 3, 4, and 5. For the sake of clarity, these are just 1 byte buffers. Think of them as just 1 byte placeholders in a buffer. So my buffer here is 5 bytes. Obviously impossibly small, but I'm not going to sit here and draw 128,000 byte buffer. Okay, so it's 5 buffers, 5 byte buffer. And when we send out this, so this is the application. So think of this as a Word document that just sent the print job to the printer. And it constitutes 5 bytes. That's all it is. It's just, a Word document that's 5 bytes in size to the printer. Remember the application dumps, remember this application that dumps it into the TCP to say, hey, send it to the other side for me? Remember that? Okay. So the application trusts TCP to deliver it, and TCP does not have the luxury of going back to Word and saying, hey man, that print job that you sent, I lost those packets. Can you reprint for me? That can't happen. All right, and this is where the guaranteed delivery of TCP comes into play. Okay, so the application, remember this is the printer job that sent it to the TCP send buffer, and what TCP does is he sets aside 5 bytes in his warehouse. Okay, he's got slot for 5, room for 5 people. And that's it. At this point, his warehouse is full. His buffer is full. He can't accept any more data from the application. And what he does is he starts to packetize this. Actually, technically, he doesn't do it. He gives it to IP, and then IP packetizes it into Ethernet frames. Okay? So I'm going to take some artistic license here, and we're going to do one-to-one mapping. That's actually not how it happens, but for the sake of simplicity, we're going to say that these 5 bytes become packet number 1, 2, 3, 4, and 5. Okay? The reason why I do that is because that makes a sequence number analysis very easy to do before we get into the real sequence numbers. All right? So these sequence number, which is nothing more than byte. Sequence number represents, there's nothing magical about TCP sequence number or acknowledgement number. All it is how many bytes have I sent to you? That's it. In this case, the sequence number is 1 byte, 1 byte, 1 byte, 1 byte, 1 byte, 1 byte. Okay? And they add up to 5. That's all. Okay? So bear with me, because this is an important concept when you're doing performance analysis, and then I promise we'll get to WIreshark in just a second. All right? So these 5 packets are on the wire and they're going. And on the receiver side here, he has 5 buffers that he can receive at any moment in time. Why? Because it turns out that Ethernet, TCP IP, can transmit faster than most applications can receive data. So think of this as the waiting room. Okay? Why do I say it's the waiting room? Because I don't know about here, but in the US, when I go to my doctor's office, I sit in the lobby. That's a receive buffer. Okay? And then they call my name, and I think, yes, I'm going to go see my doctor now. Nope. You go to another room, and you wait again. Those are buffering. Okay? When you go to the airport, and you're getting ready to check in, and you snake through that like cattle, right? Why is that? They're buffering because there are less agents than there are passengers. TCP works the same way. This client that's receiving the data doesn't have as much power as the receive buffer. So all of this is just a waiting place to buffer the data so that you can receive more than you can process. So when these packets are flying through the air, going to the receive buffer, let's assume that this packet number 3 gets lost. Okay? So when the packet number 3 gets lost, the receiver sees 1, 2, 4, and 5. And the TCP stack on the client says, wait a minute, where the hell is 3? Because I'm counting the number of bytes, and they all have to be sequential, 1, 2, 3, 4, and 5. And yet, that didn't happen, so I know that 3 must have gotten lost. Right? Makes sense. Okay? So we'll talk about that in just a second. Let's go back onto here to the server side. So there's a feedback mechanism. And what's that feedback mechanism called? Acknowledgement number. So in TCP world, we call this the acknowledgement number. Okay? And I'll explain that in just a second why that's important. But the feedback says, hey, number 3 went missing. Okay? So what does this TCP do? The send buffer is there that has the original copy of that data. So if I go back into my buffer here, 1, 2, 3, 4, 5, I erase 1 and 2 from my buffer. Why? Because the feedback that said, hey, where's 3, means that 1 and 2 was delivered. There is no question that 1 and 2 got there because the receiver is asking about 3. So I clear this buffer out, and then I retransmit 3, 4, and 5. Okay? Why do I retransmit 3, 4, and 5? Because until something called selective acknowledgement came around, TCP was stupid in a way because it just says, I'm going to trust that you got 1 and 2 and then assume that 3, 4, and 5 is lost, even though 4 and 5 made it just fine. Okay, and this is where selective acknowledgement comes in, and John Piddle has a session Thursday afternoon on how selective acknowledgement works, so I'm going to skip explaining that for now. Okay, so TCP just retransmits up from 3, 4, and 5, which seems like a kind of a waste of time, right? Because 4 and 5 got there, but TCP doesn't. Again, this is what selective acknowledgement is there to acknowledge. Any questions on that so far? Okay, so let's review some concepts before we look at the packet trace file, okay, and put this into action. Why is this important? There are a couple of reasons why this is important, which is, what's your maximum throughput? How do you calculate your theoretical maximum throughput? Anybody know what the theoretical how do you calculate the maximum throughput of TCP? So speak up for me if you could. So you still have to speak up. I have a little bit of hearing, or unless you guys can relay the message to me. Bandwidth delay product. Okay, so someone jumped straight ahead and gave me the answer, which is called bandwidth delay product. You can Google that, okay? It's called BDP, bandwidth delay product. And is that what you were saying, bandwidth delay product? Okay, thank you. I'm sorry, I couldn't hear. But let's talk about it a little bit more in a simpler terms, okay? So bandwidth delay product, what does that mean? You can only transfer 1 full window size per round trip. You can only transfer 1 full window size per round trip. That's the rule. So what's the window size that we're talking about? Send or the receive? It's actually kind of both, right? If you remember this diagram, you have the warehouse here. Okay? What if your warehouse was only 2? How many can you send? 2 bytes. Because without these 2 being guaranteed, think of this as shelf space on a warehouse. Okay, they're little bins of data. And your shelf space only has room for 2 bytes. That means you can only transfer 2 bytes because you have to guarantee, you have to go back into the bin and get bin number 2 if that goes missing. Okay? The good news is, in almost all cases, the send and then the receive buffers are the same. Most applications, when they open up a socket, they allocate send and receive buffer, and they match up. Only once in my career, there was a Unix administrator who modified that command because he realized that he sends more than he receives. So to optimize how much memory each socket's going to use, he artificially reduced the receive buffer. Okay? I'm sorry, yeah, so every socket that opens a connection requires a send and a receive buffer because TCP transmits and receives at the same time. Okay? Does that make sense? All right, so let's go into why I said you can only transfer 1 window size per round trip. Same thing. Okay? So we have server here. We have client here. Okay? So we're going to use same thing, 1, 2, 3, 4, and 5. So my window size is 5. Okay? The latency between the 2 is 1 second, which is impossibly long, but it makes my math easier, so that's what I'm going to do. Okay? Which means my round one way is half a second, and it takes half a second to come back to me. Right? Okay. When I said you can only transfer 1 full window size per round trip, this is why. I'm going to put some more buffers here getting ready to go. So that's 6, 7, 8, 9, and 10. It's not on the wire yet because there's only room for 5. Okay? And this application is going 5 my ass. I got a lot of stuff here. I got all this data queued up. This is all queued up. Okay? Because I can only transfer 1 full window size per round trip. Let's see why. These packets, 1, 2, 3, 4, 5, are in flight. And how long does it take to get to the client? How long does this first packet that left the station take to come to the sender or the client that requested the data? Half a second. Okay, the in-flight time is half a second. So at time 0.5 seconds, the first 2 packets are received. And the rule of TCP says, which I'll show you in just a second, when you receive the first 2 packets, and this is where I take artistic license, it's not really packets, but first 2 packets, you acknowledge. That's the positive feedback, right? So how long does that take? And remember, keep in mind what's happening right now. So let me draw this back out, because this concept is important if you're doing performance analysis. 1, 2, 3, 4, 5. This is my shelf. This is my data that's in my warehouse that I need to hold on to in case these packets get lost. For right now, we're going to assume nothing gets lost. I can't transmit anymore because my shelf is full, right? Because I can't accept more data because I need to guarantee these 5 bytes as being delivered, and I can't clear them out until I get positive acknowledgement they got to the other side. So it's been half a second for this data to come to here. After the first 2 packets show up, I send what back to the server? Acknowledgement saying, hey, I'm good up to first 2 bytes. Packet 1, packet 2. Byte 1, byte 2. I'm good. How long does that take to get back? Half a second. Right? So, stay with me here for few more seconds, and then at 0.999 second, has the server seen that acknowledgement yet? No. It's right at the doorstep, but the server hasn't gotten the positive acknowledgement yet, which means he cannot clear out 2 more shelf space. Does that make sense? At 0.10 seconds, the acknowledgement for 1 and 2 shows up to the server, which means, so we had 2, 3, 4, and 5, and we had 1 and 2 here. So when the acknowledgement comes in for packets 1 and 2, what can the server do? He can clear this out, and do what with it? Fill in byte number 6, byte number 7. And the cycle repeats. Okay? And so this is why you can only send 1 window size per round trip to ensure that there's guaranteed delivery. So what's the bandwidth delay product about? It's a simple math of find the lowest bandwidth along the path, multiplied by the delay, and that guarantees you what? Let me visually show you what that bandwidth delay product looks like. The bandwidth delay product is nothing more than one, 2, 3, 4, 5, 10, whatever that number is. Bandwidth delay product says, fill the pipe, okay? Instead of having just these 5 and empty spaces before and after, fill the pipe so that you can fill the pipe, get maximum throughput. But why is it that they say 2 times bandwidth delay product is recommended? Anybody know? There are a couple of things that happen when you're doing performance analysis. And that is, we live in a world where we have routers and switches along the way. So when we say bandwidth, the minimum bandwidth is 10 megabits, for example. It's not really 10 megabits or even 100 megabits. Okay, so let's say this is the bandwidth that we talk about. Remember, we're in network engineering. For most of you are in network engineering, so we talk in terms of bits. Application folks talk in terms of bytes. Okay, for us, 1 kilobits means 1,000. For application, 1 kilobyte means 1024. Right? Keep those numbers in mind because when you're writing a report, they can, you can be off by 24 bytes for every K kilobits, kilobytes, even if you transfer, divide by 8 or multiply by 8. All right, and we'll see why that's important in just a second. The reason why people say bandwidth delay product and then multiply by 2, there's a couple of reasons. One is that there's buffer lengthening along the way. Every device, every switch, every router has a buffer, which means when you have 4 hops, each one of these guys has buffer to queue up the data. Okay? So when you're doing TCP analysis and you send all these packets, every one of these devices can queue up 5 more buffers. Okay? Which means we just increased our buffer by 20, which means from TCP's perspective, he's got 20 more bytes worth of space than what the bandwidth delay product calls for, because every device along the way can buffer that data. Buffering is good, but it breaks TCP. Because TCP is feedback. There's flow control for TCP, right? So when TCP says, hey, I think the bandwidth along the way is 10 megabits and I'll use all of that, it's not really 10. TCP thinks it's 10 megabits only because there are routers and switches buffering packets along the way. It could be just 8 megabits and there's 2 megabits worth of buffering that's happening. Okay? So be aware that as network engineer guys, you might want to increase the interface buffer. That buys you a little bit of wiggle room, but in the long run, it can and make your problem worse. And I don't know if Vladimir has a session that I think is called the thing called buffer bloating, where everybody thinks life is great because I have this massive bandwidth, and turns out that's not the case. Okay? And increasing the buffer, it's give and take. Increasing the buffer gets you out of trouble in the short term. In the long term, it can blow up the network. And that's called buffer bloat. Okay? Any other questions so far before we look at packet traces? Everybody's good on the basic? Yes, question in the back. Please.
Why does the acknowledgement after the second byte?
Why did the acknowledgement acknowledge the second byte? That was a question, right?
Why not after the fifth? Or is it trying to pass the buffer size? Sorry. You said that the acknowledgement comes after the second byte. Why after the second? Is it just...
Okay. So the question was, I'm going to go back to my microphone. So the question was, why does the acknowledgement come after the second byte? So this is the artistic license that I used, because in reality, unless you're doing telnet, no one's really sending 1 byte packets. So let me show you from a real world trace file what that looks like, and we'll get to it in just, actually, you know what? I'm going to draw it out first. So the rule of TCP says, so remember there's 1500 MTU, right? And the 1500 MTU has headers for IP, TCP, etc. Okay? So just for now, assume there are 1500 bytes, 1500 bytes. Okay? There's a concept of, so this is the MTU. Then there's another concept called maximum segment size. That's what TCP can send. So this is what the IP and IP can send. TCP has its own segmenting size because of that 1500 bytes, TCP requires headers as well. So think of this as envelopes with addresses in it. TCP has to put its own address, Then IP has to put its own address. So you're taking this data, putting it into an envelope, okay? And then you have to put it into another envelope, and then you have to put it into another envelope, and they all take space. So from the initial 1518 Ethernet frame size, everybody starts stealing a little bit of header to put its own address on there. So in the world of TCP, the basic TCP, the maximum segment size is 1460. Okay? That's the most amount of data you can put into a TCP packet. And the rule is, I'll come up to here, the rule is 2 full MSS you acknowledge. Okay? When you receive, and there's no if, ands, or buts about this rule. When you receive 2 full MSS, you acknowledge immediately. No exceptions to that rule. Okay? But what happens if you get 1460 and 100 byte? So if the packetization causes it to be 1460 here and 100, what happens? Do you acknowledge or not? Because I just said it requires 2 full MSS for you to acknowledge. What happens when it's 1460 and 100 byte Ethernet and IP packets coming in? So for now, I'm going to just say IP packets. I'm done talking about frames at the Ethernet level. It's getting confusing. So I'm going to just say packets from now on, okay? So 1460 and 100, what's the rule? Let me show you. Let me hide the thing there, and there it is. Okay, I'm going to go to a slightly easier to look at. Sorry. So those are all profiles. Let me zoom in a little bit. Adjust the columns. Okay, so the content of this is not important. I'm not used to using this mouse. That's why I'm kind of fumbling around here. Let me remove this column. Okay, this is typically what you see when you first open up WIreshark, and that's why I call it the classic. And if you notice here, so here's an example of 192.168 that sent some amount of bytes here. Okay, let's scroll down. And let's look at these 2 examples. Okay, so here's 192.168. He sent how much TCP length? 124 bytes. And then in the next packet, he sent 165. And immediately, this guy acknowledges those 2 packets. How do I know? So this is being the basic class. I'll teach you the hard way, and then I'll show you the easy way. And then I'll show you yet another easier way to do this. So the way TCP analysis works, and I'm going to answer your question right after I explain the sequence number. This is a good time to talk about sequence numbers. Sequence number is nothing more than how much byte have I sent to you, and I need to keep track of it, because if you acknowledge up to a certain byte that you receive, I know that you're good up to that point. Okay? So let me explain what that means. Let me come up here. So my sequence number, I'm at 1. This is a relative sequence number. Let's go to this packet here. So I'm starting at 1, and I'm going to send you 124 bytes. So think of this as 124 passengers getting onto the train, which means the next passenger I should send is 125, right? So if I'm sending 124 passengers, the next passenger, or in WIreshark it's called next sequence number, is 125. So passenger number 125 is where I start my count, which means if I'm starting with passenger number 125, I must have sent up to 124. Different way to look at it. Does that make sense? So the next packet you see here is sequence number of 125. Perfect. I'm starting with 25, and I'm sending 165 more, which means the next passenger I should start with is 290. It turns out that when the guy acknowledges it, he says 290. So let me go back. This guy, I'm starting at 125. I sent 165 bytes, which means the next passenger I should start with, or the next expected sequence number, is passenger 290. So let me paraphrase once more. I'm starting with 125. I sent 165 passengers more. The next passenger I'm going to start with is passenger number 290. And the acknowledgement number that comes back here says, go ahead and start with passenger number 290. And what happens down here? I start with passenger number 290. Okay, does that make sense? Okay, so that's what sequence number analysis is in a nutshell. Okay, how many bytes have I sent to you? What byte am I going to start with for the next packet? And you acknowledge by saying, I'm good, go ahead and start with passenger number 290. That's how TCP works. How many have I sent to you? I keep track of that as a sender. And then the acknowledgement says, oh, okay, you're good up to passenger number 290, which means passenger number 1 through 289 was received by the receiver, and I can start with passenger number 290. Okay, make sense? So the question was, why did the acknowledgement show first 2 packets and then there was an acknowledgement? Because the rule was 2 full MSS, you acknowledge immediately. I said there was no exception to that rule, but if we go back to this, you can see here that I'm sending, so let's use this one as an example. Let's use this as an example. Okay, here I am sending some data, 124 passenger. Go ahead and start with passenger number 125. I go to the next one. I start with passenger number 125, and my next passenger I'm going to start with is 290, which turns out to be the acknowledgement number of 290. So even though this is clearly this is not 1460, right? It's 124, and this is 165. Why did this guy acknowledge immediately? Because Microsoft said, you know what? I'm going to acknowledge any 2 packets. Immediately let you know that I received those 2. What's the implication of acknowledging the first 2 packets immediately? When you tell me you received 2 packets worth of data, in this case it's 124 and 165, and you just told me you received that right away, what can I do with my buffer space, my warehouse? I can clear that out, and I can start the process faster. So Microsoft said, I'm going to acknowledge any 2 packets. In the world of Linux, Unix, etc., it's 2 full MSS. If you send me packet that's 1460 and 100, I don't acknowledge it immediately. I just sit there and wait. Because the rule was 2 full packets, I'll acknowledge. Anything else, I wait. And that's called delayed acknowledgement. Okay? And we're going to see in just a little bit why that plays such a critical role in the TCP throughput. Any questions so far? Question in the back.
How long do you wait?
Oh, perfect question. So I just said, if it's not 2 full MSS, I'm going to sit there and wait until I acknowledge, right? Delayed acknowledgement. There are different numbers, 50, 100, 150, 200. Windows uses 200. Other servers use 50 milliseconds. It can be 100. It's also tunable. When you open up the socket, you can say, no delay. I'm not going to delay at all. I'll acknowledge every single packet. There are times when you have to do this because the application is stupid. Okay? But typically you'll see 200 or 100 or 75. And it's a way of actually fingerprinting what operating system is being used by looking at these numbers. Okay? So there's IP ID, there's delayed acknowledgement numbers, and few other numbers that you can use to fingerprint what OS it is, because different operating systems use different numbers. Okay? And you will see, if you don't, you can always derive what that delayed acknowledgement number is by looking at packet trace file. And you can kind of derive what that delayed act number is. You can actually calculate that with a reasonable confidence level. Okay? Any questions about this question? Okay. So why do we care about the acknowledgement number? Because the faster the acknowledgement numbers come back, what can I do? I can keep the line moving. Every time you acknowledge me, I can send you more if my window is full. Okay? If my shell space is full, the more you acknowledge, the faster you acknowledge, the faster I can send you back the data. Any questions so far? We have till 15 more minutes, is that right? Oh, crap, okay. Okay, so now let's talk about retransmission. Actually, we're not going to talk about retransmission. We're going to go to the delayed act behavior. Okay, so we're going to continue to build, because we talked about delayed acknowledgement. We talked about what happens when packets are not full size. So let's take a look at a packet trace example of where this can have a significant impact on the performance throughput. Okay? And this is something that you can look out for because it happens a lot. How many of you work for like a financial company? Anybody here work for a financial company? Okay, so this actually has a severe consequence when you're doing transactional stuff. Meaning, it's not a bulk FTP, it's not an HTTP GET, it's I give you some data and you give me an answer back. Okay, and you can pay a severe penalty as a result of that. Okay, all right, so let's take a look at this example, and we'll start from the beginning, and let's look at the SYN packet because this is a beginning session, so I'm gonna go back and go back to the fundamentals. Number one, the SYN is the knock on the door that says, I want to open up a connection. In that SYN packet, there are a couple of things that happens, okay? I'm going to talk about what my maximum segment size is, okay? And in this case, the maximum segment size is 1460. This is the only time this is shown, okay? However, you can derive what it is by looking at the packet trace. The other thing that happens in a TCP is the other things that TCP can do, like timestamping. Chris Greer has a blog post on how timestamping works. Okay, it's actually pretty important and from performance analysis. The other thing that can happen here is a selective acknowledgement, whether I'm willing to do selective acknowledgement or not. And the other one that's important is window scaling. Okay, those are only exposed in the SYN packet. All right, so I know I have my maximum segment size of 1460, and then here I have SYNAC, where he's answering back, and he also says, hey, this is my maximum segment size. Okay, so remember, because it's a two-way conversation. All right, and so the SYN-SYNAC happens, and then he says, okay, here's a knock, I knock back, and I heard your knock. We're ready to transfer. Due to time, I'm going to just kind of cut to the chase here, and I'm going to sort by the delta column and go all the way down and show you the impact. Look at all these delays of 200 milliseconds. There's a blog post. I'm not going to show you how to create this column because in the link that I showed you on the PowerPoint, I explained how to set up all these columns, etc. Okay? So here's a delay between the packets, and it's uniformly about 200 milliseconds. What do we think that is? Remember I said the delayed act is 200-ish, right? So I'm going to go to this packet number 446 here, and let's do a quick analysis of what's happening. Okay. So just by looking at the new WIreshark UI, which packet is this guy? So this guy has an acknowledgement number, okay? You'll notice that this is all 64, 64, 64, 64, and you'll also know that from a TCP perspective, length is 0. Length is 0, so if you look at here, length is 0, 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 length is 0. What this is 192.168 is saying, I acknowledge, I acknowledge, I acknowledge, I acknowledge. So the 10.10.10 sent me a bunch of data, and I am sitting here going, acknowledge, 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 acknowledge. Okay? Remember that diagram that I drew, all those packets in flight? I'm now acknowledging that as because 192.168 is the receiver. So which packet is this guy acknowledging? Well, there's a couple different ways to do this. We can look at the acknowledgement number here, which acknowledgement number stands for what? Go ahead and start with this passenger number, right? Which is the next expected sequence number. Remember that acknowledgement number means I want you to go ahead and start with passenger number 458982, which turns out to be the next expected sequence number from the sender perspective. Does that make sense? Okay. There's another, that's the hard way of finding it. The easier way is WIreshark puts a little check mark right here. You can notice in the upper left corner, if I zoom in, you see that check mark by packet number 430? Right? What that's saying is, when I clicked on this packet, it's saying that's what it's acknowledging. So let me ask you a question. Look at the delta time difference of this act to this act to this act to this act. I am capturing from 192.168 1.0, 1.10. Look at the delta here. It's in microseconds, 300 microseconds. It's lightning quick. It's not even a millisecond. We're in the realm of microseconds. I'm saying, got it, 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 got it. And then for 200 millisecond-ish, I say nothing until I say, got it. Why is that? Because if I do the math, size of the packet. So let's go see the size of the packet. Okay? So 446 is this guy here. And if I look at it, what's his size? 1296. What are some of the other packets that were acknowledged immediately? Okay? Which is here. What's his packet size? 1460. So this is the impact of not sending a full-size MSS. Let's rewind. These are the 1460 full MSS packets flying through the air. Okay? And you can see here the delta is 12 microseconds. Okay, meaning these are just a bunch of packets, data just streaming towards me. And I receive all these data, and then I start acknowledging, until I get the last 2 bytes of data, which turns out to be not full size. Okay, right here. Full size, not a full size. Okay, kind of like that Silicon Valley show, right? Hot dog, not a hot dog. Anybody watch Silicon Valley here? A little bit, a couple people. All right. So this is the full size, not a full size. And because the rule says you must receive 2 full MSS, if you get a full MSS and a small, not full MSS, I have to wait. So what kind of operating system is this? It's not a Windows server, I guarantee you that, because a Windows server would have immediately acknowledged this, because it's 2 packets. Microsoft is 2 packets, I acknowledge you. Linux, 2 full MSS, I acknowledge you. So now we see why Microsoft, in my opinion, made the better decision. In the world of Microsoft, I would not have wasted almost 200 milliseconds in acknowledging this. And until this is acknowledged, the other guy can't clear out his shelf space and he can't continue moving the line. So what happens? I sent all this data and I can't clear out this final guy because I haven't received an acknowledgement yet. And how long does it take to receive that acknowledgement? A round trip time plus the 200 milliseconds that this guy waited before acknowledging me. Okay, that's called a delayed ACK. Does that make sense? So you're thinking, 200 milliseconds, who cares? Unless this happens 10,000 times. How much is that? 10,000 times 100 milliseconds, 200 milliseconds. Now we're talking significant delay. Okay? So then what's the answer? What can you do to get the most optimal TCP window size? Are there things that you can do to tell the application guy, hey, your application buffer size, you should make it this in order to eliminate this odd number of packets? And the answer is yes, you can do that, which we'll hit upon in the next session in 15 minutes. I'll start to build on it. But in reality, you can't. Right? Because you can't control how much the application is going to send. This is where the performance engineering and not packet analysis comes into play. There are times when you can do things like, I want you to reduce your delayed ACK timer to 5 milliseconds. In which case, you're only paying a 5 millisecond penalty instead of 200 milliseconds. In one use case, I had no choice but to turn off delayed acknowledgement, meaning acknowledge every packet. Okay? Historically, why did they say acknowledge 2 full MSS? Guess. Anybody? Steal bandwidth problems? Is that? Save bandwidth, exactly. Okay? But in this day and age, who cares about 64-byte packet? Nobody. Nobody cares about 64-byte packet. So modern day network, because bandwidth is pretty big, there's almost no penalty in sending these acknowledgments. So in one transactional application where there was a delayed acknowledgement being paid because the sender only refused, the sender sent tiny packets. That was it. So the sender would send 100 bytes and then expect an answer before sending the next one. So every time it sent a packet, guess what? There was a 200 millisecond delay. And then the guy would get tired of waiting, saying, okay, I haven't heard from you, I'll send you an acknowledgement. And then the sender would send another packet, and then we waited another 200 milliseconds. The only way to get rid of that was to change the delayed ACK timer to be, you know what? You have no delayed ACK. Go ahead and acknowledge every single packet that you get. And then we sped up that application. Okay? However, in the real world, the motivation for the delayed acknowledgement was to save bandwidth in going to the other side. Okay, the acknowledgement going to the other side. So I have a thought question for you. And this is how you know you really understood what it is that I was just talking about, which is okay if you don't get it. When you go back and listen to this and you do packet analysis and do this for yourself, you'll start to answer these questions. What happens if this packet that I highlighted, 437, goes missing? This packet has no data whatsoever. He's not sending any data back to the sender. This is just nothing more than an acknowledgement packet, a naked ACK, as I like to call it, no data. What if packet number 437 goes missing? What's the consequence? Retransmission? SAC is not enabled, so right now we'll assume there's no SAC enabled. Okay. All right. Any other answers?
I think that all the other packets will be retransmitted if SAC is not enabled.
Okay. So let's break this down in the few minutes that we have, which is actually right now. So I'll do it in 60 seconds. There is no retransmission. There's no retransmission because there's no data being sent. You cannot retransmit no data. Remember, 192.168.1.0 is sending a packet with no data. How can you retransmit no data? So there is going to be no retransmission. This is nothing more than I'm good up to this passenger. You go ahead and start with this passenger. The next one says, go ahead and start with this passenger. The next one says, go ahead and start with this passenger. That's all it's doing. So, if this packet that I highlighted, 439, goes missing, nobody cares. Why? Because the next packet says, go ahead and start with 7246, 437246. Okay? Let me rewind. And I'm just going to read out the last 4 digits here, okay? Because I'm lazy. Go ahead and start with 4326. That's what this is saying. Go ahead and start your transmission with passenger number 4326. This goes missing. This packet gets lost. And the receiver sees this one, which is go ahead and start with passenger number 9946. He clears out the shelf space. This one goes missing. I never saw it, but then this comes in, which means I can clear it up to passenger number 7246. So the fact that this acknowledgement went missing, there's zero consequence because TCP is inclusive. I am good up to this. So in fact, I can start from here. Every one of these packets can go missing, but if this one is received, then I am good up to here. So I've caught up, and I don't care about these packets going missing because these are nothing more than acknowledgements. Okay, does that make sense? Question? If you're missing 2 acknowledgement, in this bulk transfer where you have 10 of these in a row, nothing. I can miss every one of these except for the beginning and the last one, and it doesn't matter because when I get this one, I clear it out up to and including whatever this acknowledgement number says. It must, no. So the question was, the packet was lost, so you must send it again, and you don't because there's no data. Retransmission only kicks in if you sent the data. Okay? The sender has to retransmit. This is the view of the receiver, 1.10, saying, I got it, I got it, I got it, I got it. And no one cares if that I got it message goes missing. Nobody cares. Okay, that's a perfect thing, which is the sender, at some point, if every one of these goes missing, the sender, what does the sender do? He waits forever? No, he does not. Okay? Give me 1 second. Yep, that's the answer. It's called RTO, which is, so I'll hit on this topic real quick because it was going to be part of second session. So the question was, and I said, remember I qualified myself. I said, there is no consequence if I receive the first and I receive the last one. Why did I qualify that? Because everything in the middle doesn't matter because it's inclusive. I'm good up to this 48, 49, or 89, 26 byte count. But what if every one of these acts go missing? Then what happens? The sender can't sit there and wait forever. So here's what happens. Every time I send data, I start a counter, okay, based on the round trip time. And that's called the retransmission timeout. If I send you data and I don't hear back saying you got this, if every one of these acknowledgments goes missing, every one of them, I sit there and I wait and I wait and I wait, and I wait for a retransmission timeout to occur, and then on my own, I will retransmit. On my own. And that's called the retransmission timeout, and there are actually severe consequences to that, because I actually drain the pipe, I clear out my congestion. There's a lot of performance-related issues, which we won't get into just yet. Okay, does that make sense? So, let me just recap. When I'm sending you data, you acknowledge. As long as you keep acknowledging me, I keep the line moving. When a couple of acts go missing, nobody cares because TCP is all about inclusive. So this acknowledgement number is inclusive. So the fact that these 5 went missing doesn't matter because this is up to and including this guy. Up to and including this byte number. So all the acknowledgement previous to this getting lost doesn't matter. If they all go missing, the sender waits for a retransmission timeout and then retransmits on his own. Okay? Does that make sense? Okay, so we have a 15-minute break. The next session is more use cases, which we progressively get a little bit more difficult, but not that much more difficult. Okay? There are some interesting use cases that I'll show you related to this concept and others. Okay, thank you very much.